Let's see, last time we left off with this theorem, that was 27.11, I think was the number, and it said, let me make sure I got that right. Yeah, so if you're working over a field, right, then f bracket x mod polynomial is a field, if and only if the polynomial inside here, right, the polynomial that generates the ideal is irreducible over f, of course. So now what I want to do is look at an application. What this is going to allow us to do is construct lots of fields, right? Every time we know that we have an irreducible polynomial, set up this quotient right here and we're guaranteed that we have a field. And what we can do then is we can actually kind of get specific about the size of the field, right? So this allows us to construct fields of interest. So let's say it like this, so application of 27.11, and the application is constructing fields. So we're going to do this. I'm just going to do an example here. So, and this example, it's a field with 8 elements. Right? For the most part, when it comes to finite fields, what do we have? We have ZP, and then I think I did ZP. I did Z, what was it? I want to say Z3 bracket I. Right, this one has order 9. So we know a field of order 9. We know fields of order P, where P is prime. And now we're going to construct one that has size 8. And this is actually going to suggest a general technique for constructing fields. So it goes like this. What we first want to do is I want to look at the polynomial x cubed plus x plus 1. All right, living in z2 bracket x. Now, if I take 0 and plug it in, I get 1. If I plug 1 in, I also get 1. And so what that tells us is, because this is a degree 3 polynomial, this polynomial is irreducible over z2. Right? So this has no zeros in Z2, and so is irreducible over Z2. So then, by our previous theorem, right, so it follows that Z2 bracket x mod the ideal generated by our polynomial x cubed plus x plus 1 is a field. And so then the question becomes, all right, how many elements live in this field, right? How many elements are there? Right? So here's the way to do that. We want to get a handle on the size. And the idea is to just apply the division algorithm. So using the division algorithm, Z2 bracket x. Well, let me be a little bit better about this. If f of x is in Z2 bracket x, then, okay, so what would happen? We could write f of x as x cubed plus x plus 1 times some other polynomial plus a remainder, and that remainder will have degree strictly less than 3. So then f of x is equal to x cubed plus x plus 1 times some q of x plus a polynomial of degree 2 or less. So that's going to look like an a plus bx plus cx squared for some q of x in z2 bracket x, and so the a, b, and c are going to come from z2. So a, b, and c in z2. Okay, so that means then so how do I want to say it? So let's notice, right, that this right here lives inside that ideal right here, right? That product right here. So we can say it follows that z2 bracket x mod the ideal generated by x cubed plus x plus 1 is equal to the following set. So I'm going to write down a set of coset representatives basically. So a plus bx, well, I guess a set of cosets, x squared, plus the ideal generated by x cubed plus x plus 1, where a, b, and c are elements of z2. Right? So this completely characterizes the cosets living in here. And then how many choices are there for A? There's 2. How many for B? There's 2. C, there's 2, right? So there are 2 times 2 times 2 different cosets living inside here. Right? So since there are 2 choices for each of A, B, and C, we have that the order of Z2 bracket X mod ideal is equal to 2 cubed. And I mean, you should actually be able to see how this is going to generalize immediately. Anytime we have a prime p, so I'm going to write this down. So this suggests a method of computing fields of order, say p to the n, where p is any prime, and n, right, is any natural number. What do? You look at ZP bracket X mod ideal generated by some f of x, where f of x in ZP bracket X is irreducible of degree n. So this is fun. That was an exclamation point because I'm excited. We'll put 2 of them. I can put a smiley face. So, sorry. This is what happens when you're stuck in your office all by yourself, no one else to talk to. So, anyways, so this tells us how to create. As long as you can find a degree n polynomial that's irreducible, which I bet you could. In fact, there's a formula. Gauss has a formula. It tells you the number of irreducible polynomials of degree n over zp. So there's a formula that actually tells you how many different polynomials there are, irreducible, degree n, living in zp bracket x. We're not going to go into that, but so not only is this theoretically nice, it's actually implementable, right? Remember Euclid's lemma? Just sort of reminder. I mean, we already have this. So Euclid's lemma says this: if P is prime and P divides the product A times B, then P divides A, or P divides B. And now I can't even remember. Did we prove that in this class or in maybe it was back in 481? Yeah, it must have been Math 481, right? So we've known this fact. We've had this fact. You probably saw it in number theory also. So just keep that in mind, because it turns out that suitably stated polynomials have a similar property. So first, let me say this. Here's some notation. So let's let f of x and g of x be in some f bracket x. Then we say that f of x divides g of x. And I use this same slash that we use here. So f of x divides g of x if there exists, say, h of x in f bracket x such that g of x is equal to f of x times h of x. Same thing you'd expect, right? Now, I think we could rephrase this and this, or this, because of this, in terms of ideals. So let's say it like this. So note that f of x divides g of x. So what does this mean? Well, look at this. So who is, all right, so what does this say? It says that g of x lives in the ideal generated by f of x. All right, so note that f of x divides g of x. That's how I want to say it. If and only if g of x is in the ideal generated by f of x. So we can say this concept or phrase this concept of divides in terms of ideals. And okay, so I want to write the theorem here, sort of right next to my Euclid's lemma. So this would be theorem 27.12. So let's let f be a field, and let's say p of x in f bracket x be irreducible over f. Then, or let's say so now if oh yeah, that's fine. Irreducible and p of x I want to turn this into one sentence. Let's see if I can phrase things a little bit better. So let f be a field, comma, P of x in f of bracket x irreducible over f, comma, and let f of x and g of x be in f bracket x. So yeah, sorry, I was going to phrase that a little better. So there's my first sentence. And then it goes like this. If P of x divides the product f of x times g of x, then P of x divides f of x, or P of x divides g of x. And now you're supposed to be looking up here and saying, you know what, this looks exactly like Euclid's lemma, except now we're phrasing it in terms of polynomials instead of integers. And so up here, we insist that the thing that's dividing be a prime number. Notice what's happening here. Irreducibility is playing the role of prime, right, when we're working over the polynomial, or working in a polynomial ring. So for the proof, let's see. If P of x divides this product right here, then remember how we phrased divides in terms of ideals. So if P of x divides f of x times g of x, then the product f of x times g of x is an element of the ideal generated by P of x. Since P of x is irreducible, let's see, so irreducible polynomials correspond to maximal ideals. Every maximal ideal is prime. So since P of x is irreducible, the ideal generated by P of x is prime. And so by definition, f of x is in this ideal or g of x is in this ideal. P of x is prime, and so f of x is in the ideal generated by P of x, or g of x is an element of the ideal generated by P of x. Therefore, P of x divides f of x, or P of x divides g of x. Ha! Now, that is, you know, you have to admit, this is slick. That just kind of brought tears to my eyes here. Can you actually see? No. Not really. Well, no, actually my eyes are watering, but I'm not sure if it's because of itchy eyes from chalk dust or amazement at how slick this proof is. I like this. I don't know if you can tell, I'm just like, I feel a little bit loopy today, I guess. I don't know. I'm just enjoying myself. Anyways, I thought that was pretty fun. Let me state a quick corollary here. Let me check the time also. Okay. So we can generalize this easily. There's nothing to prove here. So corollary 27.13. What this is going to say is if you have an irreducible polynomial dividing some product f1, f2, f3, f4, and so on, then it's got to divide one of those. So, so as a corollary, if P of x in f bracket x is irreducible over f, capital F, and, or comma, let's say, and f1 of x dot 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 up through f sub n of x in f bracket x are such that p of x divides the product f1 of x dot 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 f sub n of x, then p of x divides f sub I of x for some 1 less than or equal to I less than or equal to n. And the proof here is just a straightforward induction where our theorem is the base case. I've got one more result that I want to cover today. And this one, I mean, if you notice, I typically stick pretty close to how the book has, the book's organization. But this is one example where this theorem that I'm about to write down actually comes from chapter 23, even though we're now in chapter 27. Right? So this is, I'm going to label it as theorem 27 I guess we're at 14. But it actually in the book, so this is from chapter 23 of Fraley, right? This is just one case where I think it's organized. It would be better. It just fits here better. So it goes like this, and it's kind of a mouthful to state. So let's let f be a field, and then we need a polynomial, a non-constant polynomial. So let's say and let f of x be a polynomial with coefficients in f, where the degree of f of x is greater than or equal to 1, right? So we want it to not be a constant polynomial. So then there exist irreducible polynomials let's say p1 of x up through p sub k of x in f bracket x, such that f of x is the product p1 of x times p2 of x dot 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 p sub k of x. So what this is saying here is that every non-constant polynomial can be expressed as a product of irreducible polynomials. And if you remember earlier, I was saying something like polynomials have our last theorem, right? Was saying polynomials have a version, or this it was I'm stumbling over my words here. Theorem 27.12 was a polynomial version of Euclid's lemma, right? That somehow irreducible polynomials behave like prime numbers. Here's another one. This should remind you of the fundamental theorem of arithmetic, which says that every number, right, every integer can be expressed as a product of primes. So here what we have, this is kind of a version of, right, the fundamental theorem of arithmetic, but we're stating it in terms of polynomials. Every polynomial can be expressed as a product of irreducible polynomials. Now, I'm not done with a statement here. This is essentially unique, right? It's the only way you can do it. But we have to say that kind of precisely, actually really precisely. So, moreover, if there exist irreducible polynomials, let's say q1 of x up through q sub m of x, such that f of x is equal to the product q1 of x, q2 of x, dot, 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 up through Q sub m of x, then, first of all, k has to equal m, right? So the number of factors in expressing our polynomial as a product of irreducible polynomials is unique, and I can't claim that Q1 is one of the P's and Q2 is one of the P's, but it's almost one. So we'll say, and, let's say this after reordering. Okay, that's good. And after reordering, Q, which one I want to go? Pi is equal to, okay, now P sub I of x is equal to alpha I times Q sub I of x for some unit, so some alpha I in F star. So we can't say that they're exactly the same. P1 may not be exactly equal to Q1, right? But after reordering, they're basically the same. One is a constant multiple of the other. So the only difference is you pulled a unit, right, out of Q1 to get P1. Or I guess I'd say it's better. You multiplied Qi by a unit to get Pi. Okay, so there's the statement, and there's really two statements here. There's an existence statement and a uniqueness statement, and we're going to prove each one of those separately. So first we'll do the existence. And so it goes like this. Well, okay, so we start off with f of x, and maybe f of x was irreducible at the beginning. So if f of x is irreducible, then we're done. If not, then we can express f of x as a product of a couple of polynomials whose degrees are both strictly less. I'm going to call them g and h. So otherwise, f of x is equal to g of x times h of x for some g of x and h of x in f bracket x, where the degree of g of x and the degree of h of x are both strictly less than the degree of f of x. Fine. Okay, so we factored it. Now, if both g and h are irreducible, then we're done. We've expressed f as a product of irreducibles. Otherwise, right, if they're not, if one or both of them are reducible, then we can factor each of those, where the degree will go down again. And so we can repeat that process. So it goes like this. So if g of x and h of x are irreducible, we are done. Otherwise, repeat this process on, well, one or both of them. So we'll say on g of x and or h of x. All right, so write g of x as a product of a couple of polynomials. Write h of x as a product of a couple of polynomials where the degrees are both strictly less than g and or h. If they're all irreducible, great, you're done. If not, repeat that process again to those component pieces, to those factors. Eventually, this process has to stop, right? Because you can't go below 0, right? So at some point, you're going to get to degree 1 polynomials, right? And then you can't split them down any further. So this process eventually stops. Right? This process eventually terminates. right? And I guess let me say that terminates with the desired factorization. Right, eventually factorization. Right, eventually they all have to be irreducible, right? Because otherwise you would continuously split, and the degree would have to go below 1, which we're not allowing. Okay, so there's the existence portion, and now for the uniqueness. So let's suppose that we have a couple of different factorizations. So suppose that f of x is equal to p1 of x dot p sub k of x, which is equal to q1 of x dot q sub m of x, where they're all irreducible. So where all pi of x and qi of x are irreducible over f. All right, so now thinking of this equality right here, what we have is that p1 times some polynomial is equal to this stuff right here, which tells us that p1 divides this product. So then p1 of x divides q1 of x dot qm of x. And then by our previous corollary, so that would be, I think, 27.13. So by 27.13, p1 of x divides q sub I of x for some 1 less than or equal to I less than or equal to m. All right, so p has to divide one of them. Now, what we can do is we can assume, right, by reordering these if we need to, that p1 just divided the first one, right? Otherwise, if it divided the 12th one, put the 12th one up at the front to start with and call that q sub 1. So by reordering if needed, so by reordering if needed, we can assume that I equals 1. All right, so what does that mean then? Well, if P divides Q1, right? So then we have that Q1 of x is equal to P1 of x times, let's say, G1 of x for some G1 of x in f bracket x. Okay. But now we need to use the fact that Q1 is irreducible. Which means that if you can factor it like this, one of those two has to be unit, and we know that P1 is not a unit. Right? So since P1, let's say since Q1 of x is irreducible, and P1 of x is not a unit, we conclude that that what? G1 has to be a unit, so that we can say that G1 of x is equal to, say, alpha 1 in f hat. G1 has to be a unit. Now, keep going, Oh, right. Okay. So now, okay. So not keep going. So now we have so now we have P1 of x dot 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 P sub k of x is equal to, now what I'm going to do is replace Q1 with P1, or I'm going to write it as alpha 1 times P1. So this will be alpha 1 P1 of x, and then it'll be Q2 of x dot 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 Q sub m of x. Now we can apply cancellation. So applying cancellation, right? We know that f bracket x is an integral domain, so we can cancel. So applying cancellation, we get P2 of x dot 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 P sub k of x equals alpha 1 Q2 of x dot 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 Qm of x, and then we can just repeat the process, right? P2 has to divide somebody over here, just assume that it divides Q2. And then, so now continuing, or repeat. And eventually what's going to happen? Well, what am I doing? I guess I'm assuming that m is bigger. Yeah, okay, so, one of these numbers is bigger than the other, right? Either k is bigger or m is bigger, and it doesn't really matter, right? So repeat to eventually get, well, I guess there's two possibilities depending on which one's bigger. So if m was greater than or equal to k, then what we would get is 1 equals alpha 1, alpha 2, eventually alpha k times q sub k plus 1 of x dot 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 q sub m of x, or if we cancel on the other side, what we'd eventually get is p m plus 1 x dot 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 p k of x equal to alpha 1 up through alpha m. And of course, I could move all this stuff, all the inverses over here. So what we would have, right? But I mean, either one of these is impossible, right? If m was strictly larger, then just using a degree argument, we'd have a degree positive argument greater than or equal to 1 here, equal to a degree 0 on the other side. Same thing. So now, since in the first case, we get, well, I don't want to say 0. So in the first case, if m is strictly greater than k, we have degree 0 on the left-hand side, but degree greater than 0 on the right-hand side, which is a contradiction. And then a similar contradiction shows in the second case. So a similar contradiction arises in the second case. All right, so what does that tell us? It tells us that k has to equal m. So it follows that k equals m and p sub I of x equals alpha I qi of x for each 1 less than or equal to I less than or equal to k. Right? So that takes care of the uniqueness portion. So here's an example. All right, let's finish off with an example. So here's my polynomial x squared plus pi times 3x plus 1. Here's a factorization. Here we're working in R bracket x. And this is equal to 3 over pi x squared plus 1. Plus 3 times pi x plus pi over 3. And both of these are factorizations of the polynomial 3x cubed plus x squared plus 3 pi x plus pi, right, which is a polynomial in R bracket x. So what happened here? This polynomial here is this polynomial, or how do I say that? This polynomial times a unit is this polynomial. This polynomial times a unit is this polynomial, right? So these factorizations are essentially unique, right? I mean, these are, or I should say, these are essentially the same factorization. All we've done is pull and slide units around.